Okay, so the next section is on tectonic plate theory, and that starts with something really important called Bergners' continental drift theory. Now, Wegener is an actual person. He was a German, amateur geologist, who had a really outrageous for the time theory about the Earth. Remember, we're talking about here in the 18th century again, where people don't really believe that the Earth has changed much. They think it's static. They don't think that rocks move. The rock cycle isn't really particularly accepted yet. But Wegener looked at some evidence and came up with this theory, and we'll talk about the evidence behind it in a second. He said that a long time ago, the continents were all joined together to form one single continent called Pangaea, and since then they have drifted away from each other. Now, his evidence for that were the three main points. This was what he thinks Pangaea would kind of look like. And if you look at it, you can see that if we try and fit all the continents together, they're a bit like a jigsaw. Okay, they fit together kind of. Not amazingly, but that's due to things like erosion. But if you look at the coast of South America and Africa, they kind of line up. You can put Australia in there in the middle. And Asia and Europe can kind of add on a little bit there to North America and Greenland. So he thought, they're kind of fitting together. Surely that can't be a coincidence. Then he found more evidence and he thought, right, I'm onto something here. He really thought he was correct, which we think he was as well. Now the first thing is that he looked at fossils. I'm going to concentrate on this coast here because this is kind of where the best evidence has been. So the coast between South America and Africa. Now there has been found other evidence for this kind of area here, this area here. So all over this is not the only point, but this is where the best evidence has been found. Firstly, he saw that there were identical fossils on the coast of South Africa and the coast of South America and the coast of Africa. Identical fossils that weren't found, say, over here. So he thought that meant these were joined together once and the same animals lived and crossed over around here and they all lived in this area. Then they died and were fossilised, and then after that, then the continent started to drift apart. So he found that there were identical fossils there. The other thing he found as well was to do with this little kind of strange diagram here. He found that if you dig into the layers of rock in South America and Africa and in these other continent boundaries that the same evidence was found in, you'll see something strange. So if you dig down, you can see here that at the top and here, the different layers of rock are all quite different. We have green, then orange, then yellow, or yellow, then green, then brown. But deep enough down, you start to see that the layers are exactly the same. So there we've got a beige, a brown, and a reddy brown. Now, this is obviously a highly diagrammised version, but he found that if we go deep enough, then the layers of rock become the same. So layers of rock, the same. Now, we know from James Hutton that the deeper the rock, the older it is. So if we go back in time, he saw these rocks formed together and then broke apart. So he thought that's more evidence for my continental drift theory. So he had three pieces of really good evidence for continental drift theory, but he wasn't believed. Now, why wasn't he believed by the scientific community at the time of geologists? Well, mainly because at that time geology based itself on things that you could see. And you can't see continents moving. Now that's because he claimed that they were too slow. But the geologists didn't like that. They said you can't see it, therefore we don't believe it. You can't see these continents moving, therefore it's not true. That was their main piece of evidence against it. Now since then, we're pretty sure that he's right. And we've kind of improved his theory and it's become tectonic plate theory, which is what we're going to go on to next. Now, but we need to think before then, we need to think about how can continents move. So Wegener had this idea that they were moving. How are they moving? Now the really nice experiment you might have done in class about this involves some golden syrup and a biscuit broken in half. This is golden syrup and this is a biscuit in half. Now if you add some heat to this underneath with a Bunsen burner, that's heat, you'll see something happening. You'll see this biscuit moves apart. The two halves of the biscuit move apart. Now we can think of this in terms of the Earth, okay? The golden syrup is like my mantle. Okay, the golden syrup is the mantle. The biscuit in half are two continents. And the heat is heat from the core of the Earth. Now, when we heat something up, we get convection currents that move around like this, okay? We get convection currents. Now these cause the biscuit to move apart, or, using our analogy for Earth, they cause the continents to move apart. Because this magma is churning and these biscuits are floating, or the continents are floating on the mantle, which is made of magma. So as this is churning because of the heat and the convection currents, those biscuits are going to start to move because they're floating on it. Now, we've got evidence that actually happens on the Earth through this. And this here is called seafloor spreading. Oh, spelled that wrong. Seafloor spreading. Now, that literally means that the seafloor is spreading out, it is moving apart. Now, if we just take this analogy and put it here, we've got here on these two sides my two halves of my biscuits and my two continents or plates. Okay, my two continents or my two tectonic plates, which we'll come on to in a second. Underneath we've got our magma, and then we've got, this is under the sea, which is why I've got a sea kind of thing here. Now, the heat from the Earth is causing convection currents, once again, to churn up the magma. And that helps, or that allows, these two continents, or the two plates, to move apart, just like we saw in the biscuit. Now, we've got evidence for that nowadays, because you might see some kind of strange, kind of vertical lines here, like this, and like this. They're a bit wiggly on the diagram. Now, these are areas of magnetisation, or where the directions are different. And you can see up here, they've been translated so you can see them in a more straight line. Now, you might know that the Earth, I'm going to draw it really quickly, has got a magnetic field that's kind of like this. And this is north, and this is south. Now, that's why compasses work, okay? The Earth is like a magnet, it's got its own magnetic field with a north and south, and it's how compasses work. When you have a compass, all it happens is that the needle points to magnetic north. If you ever have a compass near another magnet, it won't work because it will point towards that magnet instead. Now, we know that over thousands of years, the north and south pole of the Earth gradually shift around, okay? So north becomes south and south becomes north. And over the lifetime of the Earth, this has happened loads and loads of times. It takes thousands and thousands of years. It's overdue to happen right now, actually. But it's had plenty of time to do it, hundreds of thousands of times over the existence of the Earth, because it's been around for quite a long time. Now, these lines are direction of magnetisation. You wouldn't actually see lines like this under the Earth. But if you went down there with a magnet and put your magnet on these little areas, you'd see that on the grey bits, they point that way, and on the blue bits, they point that way. So these show where the direction of the magnetic field of the Earth have switched. So we know that this has happened over time. Because what happens is when the magma cools down here, when the magma cools down and becomes rock, it cools down aligned to a certain magnetic field. So if at that point in time, North Pole is up here, then it's going to cool down aligned that way. However, it then moves apart over thousands and thousands of years, and a new bit of magma comes up and starts to cool down. Now, if now, magically, not magically, actually scientifically, if by now it's changed to the South Pole is at the top, it's going to now align so that North will be down here now. It's going to now align so it's that way. So we see that gradually the magnetic field of these pieces of rock switches over time. And because of that, we can prove that these pieces of rock, these lines, were made at different times. They weren't made at the same time. And the seafloor is spread. And that is our evidence, seafloor spreading. It's really important to know about, that continents have moved. Okay, it's quite a difficult thing to understand, but this is showing us that the continents have drifted apart. It's all due to convection currents. Now, I've mentioned a lot tectonic theory, so we're going to go finally on to what it actually is. So tectonic plate theory, here we go, is simply the theory that the Earth has a crust, so the Earth's crust is split into tectonic plates, i.e. big pieces of crust. It's split into big pieces of crust, and they are floating on the mantle. So this is the theory, is that bit, okay? But the Earth's crust is split into big tectonic plates that are floating on the mantle. Now this diagram here shows you where the plates are, okay? So each of these lines is a boundary. Now we call a boundary between two plates a fault line usually, so a boundary, it's often known as a fault line. Now, these are places where things like volcanoes, mountains, trenches, earthquakes, things like that, seafloor spreading, are much more likely to happen because there's lots of activity here, there's lots of movement here. Now, they all move in different ways, so I know for certain that these two plates are moving away from each other at a rate of something like 2 centimetres a year. But because of that, then another plate, so perhaps these two plates, they think these two are sliding past each other. And these two plates might be moving towards each other. So these plates all move in different ways relative to each other, and that causes the different disasters that we know about and different things like mountains we're going to talk about on the next page. But if you think about it, this makes a lot of sense, because if you look here, now you may have heard of something called the Ring of Fire in like around the Indonesia and the Filipinos. So this is the Ring of Fire, and this is where there's like a high concentration of volcanoes, earthquakes, and it happens, as you can see these little triangles here, it happens on a fault line, because the fault line, or the boundary, there's lots of chance for magma to spurt up, there's lots of gaps for it to get up, there's lots of places for them to rub past each other to cause earthquakes, which we'll talk about in the next section. But this is one really good piece of evidence for tectonic plate theory. Also, you might have heard about the San Andreas Fault, which is around San Francisco. That's this plate here. Okay, so that's why you get a lot of earthquakes in San Francisco. Also, around Italy, there's usually quite a few. And places like that. Turkey's had a few recently, so you can see that these places have got... There's a reason why they're getting so many earthquakes. Also, New Zealand, just down here, as you've seen. These places that you know of get lots of earthquakes. China, just up there. It's because they're on these fault lines. And that's also the reason why England, or the UK, doesn't get too many, because we're bang in the middle of one. We might get a couple, because we can feel shocks from underneath from these places, or also, like, you know, there's still disturbances under the ground. But right now, we're not on a fault line. We won't be for millions and millions of years. We might move, you never know. But, or another one might be created. But we don't get major earthquakes because of this. We're not near a boundary. So, this movement, we can see they move apart, past, towards. There's lots of different ways they can move. And that's what causes the different ways that things can happen. So how can two tectonic plates move past each other? Now the first one is that they can slide under each other. They can slide under. So one goes underneath the other one, as you can see there. Now this usually causes things like trenches. So big, deep trenches under the ocean, or volcanoes. They can also push towards each other. Together. They can push together. This normally causes mountain chains. So places like the Alps, or the Himalayas especially, were created by this kind of thing. It's two plates pushing towards each other and pushing up. The third way we can have them is that they can move away from each other. Move away. And this is where we get seafloor spreading. Move away from each other. And then seafloor spreading also creates ocean trenches. This is where we get ocean trenches. And the final one, which we're going to look at in most detail, let me shift my paperwork, is this one here. They can slide past each other. And this, as is probably quite clear, causes earthquakes. And we're going to look at them in much, much more detail in the next two videos.